Afternoon, everyone. Welcome to our Ultraman CPU final project demo, and we are group 2, and the demo date is December 5th, 2010. And we have several requirements of this demo. First, there are 6 steps. Step 1 is start a simulation, and how do you load the program and data, how have you configured your caches. Here we use the MIPS code from the milestone 2, and we have an assembler to transfer this MIPS code into the machine code. So what we need to do is first copy our MIPS code and paste it into the assembler folder. Then we run the assembler. It is written by C, and after the code, the program finished, we get a new machine data. Then we copy this machine data into our model same folder, project folder. And for the data which need to be loaded into the data memory, we write the data into the TIT file previously, and we give the data that we need to save in the data memory and the address that which indicated the address in the data memory to store this data. So we need these 2 files and copy them into the project folder. Then we have all the machine code data address file into that folder. Then we open the multi-sim, and everything is compiled. And then we next I will show you some our code for this CPU. For the HDL code, we have one general CPU module which include 5 stages of on the pipeline, and this is the code for the iFetch stage. This is for the decoder stage. This is for the execution stage, and this is the memory stage. And finally, we have one read back stage. And the CPU top module included all the 5 stages. We can see here, and it also includes the logic for stall and the logic for bypass. The logic for flash is in the execution stage, and when a branch equal or jump command go into the execution stage, it will generate a flash signal and flash the command on the ID stage and IF stage. And we have one CPU test bench module which will read the machine code, the data, the address, and save them into the instruction memory and data memory. By the way, the instruction memory is in the fetch stage, and its size is 2 KB, and the data memory is in the memory stage, and its size is also 2 KB. So after the CPU loaded the data and the instruction into the memory, it will generate a finish signal, and this finish signal will send to the CPU module, and then the CPU module will generate a ready signal to tell all 5 stages on the pipeline that they are ready to work. And also in the CPU test bench stage, we can freely to change the miss rate and miss penalty, and for the CPU, and the CPU will transfer these 2 parameters to the memory stage, which the memory stage will use this 2 integer to have and there will be 2 miss counters in the memory stage to use these two integers to set up the mid store cycle and the length of the store. And the mid store, once the mid store happens, it will store the first three stages. Okay, next we'll go to the go to the step 2. Step 2 is execute your simple state program and show how you detect the hazard. So first we compile all the files, then we simulate the CPU test bench file. Then in order to show the data hazard, we go into the execution stage. Then we zoom in and change the display into the unsigned, which we can clearly see the data. So we have several types of data hazard. First, for this data hazard, you can see the store signal is active here. So by checking the MIPS code, we can find there's one data hazard in these two lines. This line means load word intermediate, which means load the data into the register file number 5, and the data's address is saved in register file number 1. And next is branch less than. So if number 5 less than number 2, it will return jump to the loop 1. So in this instruction, it needs the data of number 5 and number 2 in the register file, which the number 5 the data in number 5 has just changed by the load word intermediate. So there will be one data hazard, and so the store happens because when the instruction goes into the branch instruction goes into the execution stage, it doesn't have the update data for the number 5. So next, so it will store for one cycle. So next cycle, the data will be read out of the data memory, and this time the bypass logic will work and load the data into the execution stage. We can see here the first cycle is 1, and then when the store happens,